Now, we want to define the area of a surface. Until now, we only know how to measure the area of the flat object. For example, a triangle, a rectangle, a circle, a disk. We know how to compute the area of a flat object, even if the boundary is not straight. For example, the circle, the disk. Okay, the domain bounded by the circle. Okay, we know how to compute pi r square. Okay, but for curve object, we don't know how to compute the area. We do even not have a definition of the area of a surface. Now we will define the area of a surface. To define the area of the surface, the area of a parallelogram, very difficult to read these words, it's very important. Now we introduce what is the parallelogram. Okay, so let U and V be vector in R3. The parallelogram spanned by this U and V based at the point P is this subset, capital P, P plus TU plus SV, S and T in this open interval. So this is the definition of a parallelogram. So geometrically, this is U, this is V. So the corresponding parallelogram is this. This is P. That is this reason. Okay. So in elementary geometry or in analytic geometry, at least you have learned vector algebra. Okay. You know that the area of P denoted by AP is the norm of the cross product of U and V. Okay, this is well known. Now, suppose S is a smooth surface. With parametrization. Here D is a region in R2. So this is a smooth surface. We will want to define the area of the surface. How to do this? So this is UV plane, two-dimensional space, and D is a domain here, and maybe I will go to next page. I don't have enough space here. So our surface S has a parametrization. We want to define the surface, the area of this surface. So this is UV plane, and this is a region D, and this is R, the parametrization map. We want to, of course, the image of D is the surface S, but to make the picture brief, easy to read, easy to look, I don't draw. Maybe I will draw it. Okay, so this is S. Okay, now we take a partition. Take a partition of D. In fact, the partition also does not make sense. We only have partition of rectangle, but D is not a rectangle. Okay, we just draw some line. Using what color? Or too much color. Okay, this. Using the lines parallel to the coordinate axis to divide this, maybe I don't need so much. To divide D into small pieces, we consider a rectangle R contained in D. The rectangle is this one, red one. Okay, so this is A plus H. This is B plus K. So partition of D, and then take a small rectangle contained in D, denoted by R. A plus H, B plus K, contained in D. Consider this small rectangle. Then the image of this R under our map F, under our map R, is a small pieces of S. Right? So this piece, what color? Red. So the image of this is, I will erase the S. The image of this small rectangle R is this. This is so correspondingly this point. This point is R A B, and this point is A plus HB, and this point is A B plus H, and finally the last point is the image of this point. Okay, I will have no place to write it. So the image of this small rectangle is the image of the region bounded by these four red curve, which is the vertex. The vertex, that is the both dot 4 points, one red, 3 blue, are the image of the vertex of the rectangle. So we will approximate this image RR by a parallelogram spanned by the following vector. This is the key point. We approximate the area of RR. We approximate the area of R by a parallelogram P spanned by these two vectors. Which two? One is this, the other is this. These two vectors. These two vectors determine the parallelogram outside the picture. Okay, but I don't need to draw the picture if you want. Okay, this is parallelogram. Okay, surrounded by these two vector. This two vector is which two? This vector, this one is a plus hb minus ab. The other is a b plus k minus ab. Okay, this is the point. The image of R under the map R, that is our RR here, is a curved object in the space. We don't know how to measure its area, but we use the flat object, that is the parallelogram, a suitable parallelogram to approximate the curved object RR, the image RR. So we know that this parallelogram is bounded by the vector given here, but this two vector is still too complicated. We need to simplify it. So using the differentiability of our map R, so this is approximately the partial derivative of the vector valued function R at the point AB, then multiplying H. Similarly, the second is approximately with respect to V, K. Okay, so we have already approximated the curved object firstly by a parallelogram bounded by these two vectors. But these two vectors these two vectors are still too complicated. We use the differential calculus result to replace them. That is approximate again, the second step approximation, to replace them by these simple, good-looking, handsome vectors. Okay, therefore, after these two steps of approximation, the area of RR denoted by d sigma. D sigma will I will write more complete. We use d sigma to denote the area of RR. D sigma is the area of the image of R. This is a curved object, but the area we have not defined yet. We want to define this. So what we have in mind for the area is the area of the parallelogram of the two vector given here. The two vector given here. Okay, so the area of this parallelogram is the norm of the cross product of these two vectors. So this is almost this vector cross product with the other vector, then taking the norm, and this can be easily computed to be I will go back to the upper space. So this will equal RUAB cross RVAB, then HK, Hong Kong. HK. Okay, so we have an approximation. D sigma, the area, what we have in mind, the area can be should be approximated by this quantity. Now we link H and K. As HK goes to 0, HK goes to 0 For the infinitesimal small hk, we denote it by du dv. Because u, h, and k are the increment in the direction of u and v. Therefore, when they goes to 0, infinitesimally, we denote it by du dv. And we can expect that when when this rectangle R shrink and shrink becomes smaller and smaller, very, very tiny, eventually go to the point AB. Okay. So the area should be very, this approximation should be very much more accurate. Okay. If the diameter of R is of the rectangle is large, then this approximation, the error of this approximation will be very considerable. But when the dimensions shrink, the rectangle shrink to a point AB, then the accuracy will increase. Okay, so we can expect that d sigma is RUAB cross RV. Oh, no space to write. I should not use bold form. I will erase this, write it again. D sigma should be the norm of RU RV du dv. This is what we need. So this is a very tiny area element on the surface. You can expect that when the point AB go around the surface, we replace AB by UV. And then when the point UV run around across the region D, and then taking integral, the integral is very naturally to define the area of the surface as to be that integral. Okay, so our result is that the area of this surface is defined to be the integral of RU of this function. So this is the definition of area of a surface. Given a surface, take a parametrization R, then construct this double integral. R is a function of UV, vector valued function of UV. So the partial derivative of R with respect to U and V are still vector valued function of UV. Their cross product is still a vector valued function, but taking the norm becomes a real valued function. So the integral in this final integral is a two variable real valued function. So we can consider its integral over the region D. Therefore, the result is defined to be the area of the surface S. Okay, so this will complete the definition of the surface area.